Welcome back to Kinesthetic Knowledge 101, and I'm your host, Isha, here today for another episode on the musculoskeletal system. Today, we will explore the fascinating world of skeletal muscle regeneration. While vertebrates like salamanders can regrow entire limbs, mammals like us have a more limited regenerative capacity. This means our muscles, while capable of repair, have limitations when it comes to complete regrowth after injury. It's an evolutionary trade-off as complexity comes at the cost of some regenerative prowess. But here's the cool part. Even with this limitation, mammalian skeletal muscles retain a remarkable ability to heal and maintain themselves. The process is particularly fascinating because it shares key features with the program that guides muscle development during embryogenesis itself. Think of it like using the same blueprint for both building and repairing your house. Let's take a deeper look into the exact molecular mechanisms at play. So during this process, transcription factors act as the cellular conductors, playing a pivotal role in muscle development and regeneration. Among these, PAX3 and PAX7 establish the foundation for the subsequent action of myogenic regulatory factors, or MRFs. The MRFs, including MyoD, MyF5, myogenin, and MRF4, serve as the master regulators, orchestrating the entire gene expression program. MyF5 initiates the commitment of stem cells towards the muscle lineage, akin to a conductor raising their baton, for example. MyoD subsequently drives the differentiation of these committed cells into mature muscle cells. Myogenin appears to be critical for the final stages of muscle cell maturation, ensuring proper development. So the role of MRF4S is actually a lot more intricate and less understood. However, there is a potential for its role for influencing both muscle determination and terminal differentiation. So beyond the action of these MRFs, epigenetics also adds another layer of complexity to the process. So epigenetic modifications on histones, which are proteins that package DNA, can influence gene expression. Deacetylases and core pressor complexes act as silencers, repressing muscle genes and proliferating myoblasts through specific histone modifications. So moving on to the muscle generation itself. Muscle regeneration occurs in 5 interrelated and time-dependent phases, namely degeneration, inflammation, regeneration, remodeling, and maturation/functional repair. Starting with degeneration itself, or necrosis. So necrosis actually involves an influx of calcium ions, which disrupt the muscle fibers membranes known as the plasmalemma, and this leads to a breakdown of contractile proteins, organelles, myonuclei, etc. Necrotic cell death stimulates the host inflammatory response, leading to the next stage of inflammation. A tightly regulated inflammatory response is essential for clearing debris and initiating regeneration. Neutrophils, the first responders, arrive within hours, engulfing damaged cellular components and secreting pro-inflammatory cytokines that recruit monocytes and macrophages. These monocytes differentiate into macrophages, taking center stage by day 2. Macrophage populations are actually heterogeneous, with M1 macrophages acting as phagocytes, clearing debris and promoting further immune cell infiltration. So as the inflammation subsides, M2 macrophages will emerge, playing a critical role. They actually secrete growth factors and cytokines that activate resident muscle stem cells, known as satellite cells. We'll look into satellite cells a bit more deeply in a bit, but these satellite cells essentially become myoblasts, proliferating and then fusing to form new myofibers, which are the basic unit of skeletal muscles. So newly formed myofibers are immature and they lack the full contractile capacity of adult fibers. This phase focuses on strengthening and organizing them. Extracellular matrix components are deposited to provide structural support, while angiogenesis ensures proper oxygen and nutrient delivery. And then finally, the myofibers will continue to mature with centrally located nuclei migrating to the periphery, which is a hallmark of adult muscle fibers. Myofibril organization and protein expression reach their peak at this point, restoring contractile function and strength. It's really important to take note that the success of muscle regeneration hinges on this delicate balance between pro-inflammatory, which were the M1 macrophages, and anti-inflammatory or reparative macrophage activity, which was the M2. So M1 macrophages are activated by cytokines like IFN gamma and TNF alpha, and these can be detrimental if their activity persists. Interleukin 10 plays a pivotal role in promoting the switch from M1 to M2 macrophages, crucial for proper regeneration. So as promised, I'm going to get back to the star of the show, satellite cells. These are the resident muscle stem cells that reside between the basal lamina and sarcolemma of the myofibers. They remain dormant or in their quiescence stage until called upon by physiological stimuli such as exercises or in response to muscle injury. Once activated, satellite cells transition from their dormant state to dynamic myoblasts, which are the proliferative precursors fueled by cell division. A cool fact, or something that has gained a lot of interest in recent research, is that satellite cells have an additional layer of complexity, and that's that they divide asymmetrically. So what this means is that satellite cells will generate a daughter cell that retains its stem cell potential and another destined for immediate myogenic differentiation. This basically ensures a continuous supply of stem cells for future repairs. It's really important to understand that the success of this regeneration hinges on a carefully balanced act. So myoblasts must proliferate at an appropriate rate to generate enough building blocks for new muscle fibers. But they also need to differentiate into mature muscle cells at the right time. Signaling pathways like Notch and Wnt act as stage managers, ensuring that this delicate balance is maintained. For example, Notch signaling will ensure that these cells remain in their dormant stage, while Wnt signaling will promote differentiation. But going back to satellite cell differentiation, once they differentiate and form muscle fibers, they must mature, meaning that they must be reorganized. As you may remember from the video on muscle strength, myofibrils are highly organized contractile units. Nuclear relocation must also occur during this stage, as they're initially clustered in the center of the fiber and must migrate to the periphery, as I've kind of stated beforehand. Another key component of this stage is connective tissue remodeling, which marks the transition from initial repair phase to the maturation and strengthening of the regenerated muscle tissue. Activation of the extracellular matrix, or ECM, is important, as the ECM serves as a scaffold for the muscle fibers and provides support during regeneration. Collagen, fibronectin, elastin, and proteoglycans are among the key components synthesized during this phase, which help stabilize the tissue and guide the formation of neuromuscular junctions. Many studies have actually shown that it takes around 2 weeks post-injury to form new neuromuscular junctions. Angiogenesis, as I mentioned earlier, is the formation of new blood vessels, and this must also occur at this point to ensure adequate oxygen and nutrient supply to the regenerating muscle fibers, and therefore further supporting their growth and maturation. So overall, protective tissue remodeling is essential for the functional recovery of the muscles, as it ensures the regenerated muscle tissue is integrated seamlessly with the existing muscle, maintaining similar levels of flexibility, strength, and overall function. So in summary, what I hope to do within this episode is to demonstrate the whole muscle regeneration pathway and also show how it acts as a testament to the remarkable symphony of cells and signaling pathways working in harmony. This system is highly complex with a multitude of other factors in play. However, I have tried to simplify it as much as possible. In future videos, we will focus on what happens when things go wrong within this process. Thank you for listening, and I hope to see you next time on Kinesthetic Knowledge. Take care.